Okay, it seems like they're... Okay. So, welcome us all to the last session of today. And we have Daniel, changed position, speaking to us about succinct, non-interactive arguments of proximity.
Great, thank you. All right, so I'm going to tell you about succinct, non-interactive arguments of proximity, or SNAPs. This is a great acronym, so it's to be a great primitive. This is joint work with Lian Chen and Zheng Jin. Lian is an undergrad student at Tsinghua University. He visited us at Northeastern for summer internship last summer when we did this work, and he's going to be starting his PhD at MIT in the fall. Okay, so this talk is about proving and efficiently verifying properties of huge objects. That's the goal. And to have something concrete in mind, think of the huge object as being like the entire social network. So maybe here, I think this Instagram wants to claim that they have less than 5% of fake accounts. This might be some property that you could check if you did some careful analysis of the entire social network, you could detect this. And we want a way for Instagram to prove this with a short proof that would be easy and efficient to verify. So how do we prove this? And this is based on a true story. Like a few years ago when Elon Musk wanted to buy Twitter, this was a big point of contention, how many fake accounts there are. So this could have been useful. Okay, so...
Defining the fake account?
No, I'm not defining it. Okay, so... Okay, this is in the third day of the proofs workshop. You've heard a lot about snark, so maybe your first thought is, oh, let's just throw a snark at it. This will solve the problem. So just quickly, review. I know you've seen it a million times what a snark is, and also why it doesn't exactly solve the problem. So snark is a short, easy to verify proof that proves that some statement X belongs to a language, could be a language in P or NP. The prover gets the statement, if it's an NP language, also witness, and produces a short proof. And the verifier gets the statement, the proof, and should check it, should verify it. Completeness says that if X is in the language and everyone's honest, then the verifier is happy, accepts. Soundness says that if the prover is malicious, it should not be able to come up with a false statement and some sort of a valid proof for it that the verifier would accept. Okay, and here you can have either selective or adaptive soundness. I didn't say, but all of these proofs are in the CRS model and some common reference tree model. And you can ask for selective adaptive soundness depending on whether the statement can depend on the CRS or not. Okay, and this will be important later. And then there's a succinctness requirement, which says that the proof is short, ideally just polylogarithmic in the statement size, so very, very short. And the verifier is efficient, ideally just reading the statement and, well, the short proof. So ideally just linear or quasi-linear in the statement size. Okay, so that's great. We've heard a lot about these guys. Can we just use this to solve the problem, to verify some properties of a social network? And the issue here is that the statement itself here is the huge object. I want to say that, let's say the social network has less than 5% fake accounts. The statement is the social network. And if you use the snark, the verifier would have to at least read the entire statement, read the entire social network, which is too large and efficient. So we want to do some proof that would be much easier to verify than reading the entire statement. Okay, so the question is, can we define some notion of succinct, non-interactive arguments where the verification time is sublinear in the instance length? You don't even have to read the entire statement. And so that motivates this notion of SNAPs, succinct, non-interactive arguments of proximity. The syntax is similar. Again, you could have these for either P or NP. The prover gets the statement X, and if it's an NP language, also the witness W, and creates some short proof. But now the verifier still gets the proof pi, but it doesn't get the statement X in full. It only gets oracle access to the statement, and it should only read some small number of locations of this statement. And here we want the verifier efficiency to be sublinear in the statement size, so the number of locations it reads is small, and in particular, verifier efficiency bounds both the proof size because it reads the entire proof and the number of queries it makes to the statement. Okay, so we want both of these to be sublinear. Okay, so recall the original notion of soundness for snarks. The queries are bits? The queries are bits. Yeah, just bits, individual bits of the statement.
Can I ask maybe a dumb question?
Yeah.
Shouldn't I think of these as I'm transforming the relation into a relation where I also commit to the instance, and then I have this new relation where I'm proving an opening for the instance and then everything else.
Good, but how do I know you actually committed to the correct instance? Like I'm the verifier, want to verify some properties of the Instagram social network. You commit to something and prove some properties of that, but how do I know that you committed to Instagram social network, right? So that's kind of here, like the verifier really has access to the original statement. That's the statement he cares about. This is the statement he wants to verify properties of. Whatever you committed to, I need to check that it's committed to the right thing. Naive way of doing it would require reading all of X. So that's maybe, does that answer your question?
I mean, I'm thinking that I could just give you another Instagram network if I wanted to as an instance. But in that case, it makes me think that maybe I can do like other types of queries. But that's another story.
We'll see. So good. I think you're thinking ahead, and we'll see what the solution strategies are. But let's first talk about what security we can even home for. So recall that for snarks we wanted this notion of soundness that says that the adversary cannot produce any accepting proof for any false statement. So unfortunately, that's going to be impossible to achieve if you want a sublinear verification time, because if I just take a true statement, prove it, and then flip one bit of the statement, a random bit somewhere, it's likely to change it to a false statement, and there's no way the verifier will catch me. It's very unlikely with the small number of queries. So we're going to have to relax soundness in the natural way, instead of requiring the previous notion of soundness that you can't prove any false statement. Here we're going to guarantee approximate soundness, which says that an adversary cannot produce a valid proof for any statement that is far from being in the language. And this is intuitively useful, like if you're thinking of our example of proving that Instagram has less than 5% fake accounts. If you're close to that, then maybe you have 6% fake accounts. It's not too bad. Okay, and here this epsilon fraction, you should think of this as some sort of a small constant, like 1% relative distance away from being in the language. Okay, and so this is an interesting primitive. It has a lot of applications, like verifying properties of social networks or any kind of big data. It also does give you actually a very useful and efficient snark. If you know your statement is already encoded with an error-correcting code, then you get the original notion of soundness. Okay, and it's also fundamental as a primitive on its own. It's very related to things like property testing and probabilistically checkable proofs of proximity and so on. Okay, so what do we know about this primitive? There's been a prior work by Yael and Ran in 2015, and they constructed this notion of succinct non-interactive arguments of proximity, or snaps, in the designated verifier setting. So the verifier needed a trapdoor or some sort of secret key to verify the proof for P, for polynomial-time languages, with selective soundness and verifier efficiency, which was slightly sublinear. So it was O of n to the 1 minus gamma for some constant gamma, some small constant gamma greater than 0. It was kind of left unspecified because it came from complicated prior work. So I don't think anyone knows what the constant exactly is, but some constant. And they did this from sub-exponential fully homomorphic encryption. So this is the result that we knew since 2015. And it's a great result, but as cryptographers, we always want more. So there are like a number of aspects where you might want to improve. First of all, it's only designated verifier. Can you get publicly verifiable? It's only for P. Can you do it for NP? It only has selective soundness. Can you get adaptive soundness? And the verifier efficiency is only slightly sublinear. Can you do like really good polylog verifier efficiency? So lots of good questions. And they also gave kind of a negative result, a black box separation barrier, showing that if you had this type of snap for P with verifier efficiency that was better than square root of n, then you cannot prove it under falsifiable assumption, kind of similar to the Gentry-Wichs barrier for snarks for NP. And it's just important to put this in context. This doesn't really say that you shouldn't expect these things to exist. I mean, for snarks for NP, we do expect them to exist. It's just a barrier on how to prove their security. And nowadays, we even know new techniques to overcome these barriers in some settings.
In the random worker model, this is a simple application with what we call E plus P CPP, right?
You'll see. Not quite. Not quite. Okay, yeah. So maybe I'll say something about it. I wasn't going to. For selective soundness, yes. For adaptive, no. So when you want to make it non-interactive in Fiat-Shamir, for adaptive security, Fiat-Shamir actually needs to hash the statement. It's very important you hash the statement, and that requires linear time. So you do not get even a heuristic construction of adaptive snaps. And there's a good reason for that, you'll see. Okay, so that was the work that existed. So now it's snaps 10 years later. What do we know? There actually hasn't been really any work on this problem, but there's been a lot of work on related problems on snogs and barks. I think we have a much better understanding of many of primitives that are similar. So it's kind of time to revisit this question. And so what we're going to ask here is for what parameters and under what assumptions can we build snaps for both P and NP with both selective and adaptive security. So there's a lot of different questions, and you'll see there's kind of a lot of results. So I think we kind of give a pretty close to complete characterization of this problem. Well, there's still some good open questions, but most of these things we now know how to answer. So I'll tell you what the results are. So our first result is actually an unconditional lower bound for adaptive snaps for P, saying that you cannot do better than square root of n security. This is not a provability barrier. This is a real barrier. Like no matter what assumptions you throw at it, this just cannot be done. And so that, I think, answers your question. This is why we don't even have heuristic constructions of this primitive. It just doesn't exist.
For IPP, I mean, there are also lower bounds of square root and for IPPs, right? So
Right. So it's somewhat related as well. Yeah. Good point. Okay. So this is just for adaptive. This does not work for selective. Our result 2 is we actually show a construction that matches this. So we get adaptive snaps for P with square root of n verification time from a number of standard assumptions like either LWE or decision linear, essentially the same assumptions as snogs for P. Okay, so this kind of shows us what the best possible is for adaptive snaps for P. What about NP? Can we do it for NP as well? So here.
So the verifier square root n, is that also, I know it's upper bounds, the queries and the proof length, but is that also the actual length?
Yes. Yeah. Both the queries and the proof length will be square root of n. Essentially, the lower bound shows the product of them has to be n. So there's some trade-offs, but if you want to just do the best of the max of those, then square root is the best you can afford. So what about NP? So our third result shows that actually there's a simple way to combine snaps for P and snogs for NP to get snaps for NP. And therefore, we get adaptive snaps for NP with square root of n efficiency from the same assumptions as previously plus IO, essentially the same assumptions as snogs for NP. Okay, so that really gives us a full characterization of the adaptive case for both. We match the lower bounds we get for both P and NP under essentially the same assumptions as snogs for P and NP. The natural question is, can we do it better for non-adaptive? Can we get can we do better than square root of n verification time? Yeah.
So you can get snaps from IO?
Say it again?
You cannot get snaps from IO?
Oh, just IO without these extra assumptions?
Yeah.
We didn't think about it too hard. I would assume, yeah, we didn't think about it too hard. Good question. Okay, so can you do better if you give up on adaptive security, if you just want selective security? And so we show that you can actually get non-adaptive snaps for NP with amazing just polylog, so optimal security, just polylog verification time from strong assumptions from IO and one-way function LWE. So essentially similar assumptions as snogs for NP, but modulo you also need sub-exponential security. You actually kind of need adaptive snogs for NP to get non-adaptive snaps for NP. And so the last question you might ask is, well, this does it for NP under strong assumptions. Can you do it for P under weaker assumptions without IO, without obfuscation? And here we give a negative result. If you build non-adaptive snaps for P with better than square root of n efficiency, it would imply snogs for NP, non-trivial snogs for NP. So somehow it seems like you cannot avoid strong assumptions that would give you snogs for NP.
When you say non-trivial,
You mean like the length is smaller than n? But
Exactly. So depending on how much less than square root of n you are, that's how much less than n the proof would be. And here's the statement size. Yeah. Great. Okay, so just to put all the results in the table, we have like two columns, adaptive versus non-adaptive, P versus NP. In the adaptive setting, we know square root of n is the best we can hope for, and we get it for P under kind of the same assumption as Snarks for P, and for NP under the same assumption as Snarks for NP. For selective security, we know that you can't really do much better for P than NP because it implies Snarks for NP, and we get the optimal succinctness for NP under strong assumptions that it from obfuscation assumptions. Okay, so in the remainder of the talk, I want to tell you a little bit about just this first box about the adaptive snaps for P, both the positive and the negative result if I have time. And I want to start with kind of a key difficulty of constructing adaptive snaps that explains both the lower bound. It gives you some intuition about why it's hard to do better than square root of n, and also like the main difficulty we have to overcome for the upper bound for the construction. And here's the difficulty. I'll in fact describe a generic attack that breaks all snaps, and then I'll tell you a way around it, potential way around it. So here's the generic attack. I'm going to take a true statement x star and generate an honest proof pi for it. And let's say the verifier is deterministic. So the queries it makes to the x star are deterministic given the proof. So I'm just going to check what positions of x star of the true statement the verifier checks. There's very few of them because it's efficient. Let's say square root of n or sublinear in n at least positions. And now I can just modify every other position of x star that the verifier didn't touch and come up with some false statements that the verifier will still accept. So this completely seems to kill the adaptive setting. Here it's important that it's adaptive because I create the statement x depending on the positions the verifier touch, which depends on the CRS. So it would be an adaptive statement, adaptively chosen statement. So good. So I'm assuming here that it's deterministic. If it's deterministic, I'm claiming you really cannot do it. But yeah, you're exactly right. So how do we prevent this attack? We make the verifier randomized. If the verifier is randomized and uses fresh random coins that the prover doesn't know, that don't depend on the CRS or the proof, you might be able to get around this. And that's indeed what the positive result will have to use. But then there's kind of this additional difficulty, which is that, okay, so the verifier is randomized and checking some random locations of this statement x star, but now the proof doesn't even know which locations the verifier will check, so it doesn't tell him anything about the locations he's going to check. How can they be useful? So that's the major challenge we'll have to overcome for the positive result. And in fact, for the negative result, it kind of says if the proof is too small and you check too many locations, then they're not useful. This will not work.
So why the query cannot depend on the proof?
Say that again? The query can depend on the proof, but here the prover generates an honest proof pi for statement x star and just checks what location of x star you query. And I say, okay, now I'm going to change every other location and give you a false statement that you'll still accept, right? Does that? Oh, the last statement. Why are well, because I'm saying to overcome this negative, if they only depend on the proof, then you have this negative result. To get around this negative result, they have to be kind of random, even given the proof. So they have to be unpredictable even given the proof, right? Otherwise you have this, otherwise this attack holds.
Given the location in the proof which were looked at, the other location.
Right, so you should not be able to predict the locations the verifier will query given the proof. If you could predict them, then you'd have this attack. So somehow these locations should be very unpredictable or random even given the proof, but then it's unclear why they're useful. The proof isn't telling you anything about them. What are you checking?
I somehow don't understand the difference between the two bullets. Aren't they saying the same thing?
The top and the bottom?
No, allow randomized verification.
So this is the way to somehow prevent this attack. But this is saying even if you allow randomized verification, there's still some sort of an intuitive challenge that you need to overcome. Right? This is the intuitive challenge that now the verification is randomized. It's checking these random locations that the proof is not telling you anything about. How are you going to make that useful?
So basically saying you need to use randomness, but randomness seems to be not useful to you.
Exactly.
So you're stuck.
But this is not, we'll see how to overcome it in some cases and not in the other cases.
But the
just
query,
intuition.
The query could, in principle, depend both on the randomness and the part of the proof that you already read.
Sure, yeah.
Yeah, in
That's,
that
you
sense
could
that
do, none of our constructions have that, but you could potentially do adaptive. Yeah, we don't use that, but it could be like adaptive.
Oh, there are positive results for statistical proofs of proximity.
Good. Okay. So let me now go into the positive result, and the kind of the main interesting tool for the positive result is a new primitive that I think is interesting in its own right. It's not inherently tied to proofs or anything, something we'll call commitment of proximity. So here's a commitment of proximity. It's a way to take a long value x, long statement x, long input x, and hash it down or commit to it with a short commitment c. Here, I'm just like in the rest of the workshop, I'm using commitments for deterministic commitments. There's no hiding property. They're just short. Think hash. Okay, and there's some commitment key to make this possible. Okay, and then during the opening stage, the verifier gets a commitment key, gets a commitment C, and is checking the commitment against some input x. So when I open it, the verifier kind of checks that it's computed correctly. But it should do that without reading x entirely, by just checking a few locations of x. So kind of similar to the snap setting. And can we guarantee binding that this x is the same as the one that was committed to? Well, unfortunately not. It's impossible because, again, if I just flip one bit of x, you'll never catch me. But it will want binding of proximity. So what this says is that it's hard for an adversary to come up with two values, x and x prime, that are far from each other, further than some parameter k, some distance parameter k, such that if I take an honestly generated commitment to x, if I take some c that I can actually open as a commitment to x, a verifier would verify it given this faraway value x prime. Okay, so again, it says that if I can create commitment using x, if you're going to verify it in sublinear time with some x prime, that x prime has to be close to x. Okay. So we show how to construct these commitments of proximity from collision-resistant.
I'm slightly confused. So at some point, I somehow expected in the description to see some kind of the commitment information, but that's not what's happening, right? Like you want to.
That's not what's happening. Yeah, so the decommitment information is x itself. Again, there's no randomness. It's not a randomized commitment. So I'm kind of creating a commitment to x, and then you're verifying it against some x prime that might be different from x, and I win if these are far from each other. And
You're not talking about locally open?
there's no, I don't have a local opening here.
So even though original x is used,
Yeah.
this x is not used?
Yeah, I mean, there's inherently it's kind of locally check up because I'm doing local checks here and need to check if the commitment is correct. There's some locality aspect here, but yeah, this is the notion.
So what does V see? Sees the commitment. He has oracle access to X prime.
That's it.
And that's it.
That's it.
There's not the commitment because everything is public.
Exactly. There's no randomness or anything. Yeah.
Could you see it as like a computational version of just equality protocol from communication complexity? Like Alice sends some hash.
Sort of, but there's a proximity version aspect here, and there's some computational hardness.
Code, right? It's a
There's some
cryptographic version of locally testable code, right?
Except that it's not so efficient.
Yeah, there's no. Okay, never mind. It is what it is. You see what it is on the slide. This is simple enough. So let's not try to draw analogies. Yeah, this is it. Okay, so we give you. So we show how to construct this thing, where everything is square root of n. The commitment size and the verifier's complexity are both square root of n. And this again, you can show to be optimal. The product of these two things has to be n. And also, the distance parameter here is actually very small. It's square root of n. So usually for snaps, we're kind of OK if the statements are epsilon fraction far from some constant epsilon. We're OK with 1% distance. Here we can do much better and actually guarantee that the x prime is really, really close to x. Only square root of n changes. And this will be important for constructing snaps for us. This will be important later.
Say that again. Square root of n as opposed to what?
Epsilon n. Right? So this is much better distance. You guarantee that they're very close, not just constant fraction apart.
Essentially, epsilon equal to 1 over square root n.
Yeah. Rather than a
Parameters
constant.
are also like
Exactly. So rather than a constant epsilon, you get 1 over square root of n epsilon.
Do you care about other points on the trade-off curve?
We do, yeah. And we give a full characterization in the paper. I just didn't want to put it on the slide. So, so essentially, there's some trade-offs between the number of queries and the commitment size that you can
in
do.
Your construction.
In the construction, yeah. And there's some flexibility in that. And we actually do use some other trade-offs as well in the full construction of stamps later when we do this, but I didn't want to talk about it. Okay. So let me give you a simple construction that doesn't quite achieve it, and then we'll fix it to achieve it. So here's the very, very simple construction. I'm going to take the input x and split it into square root of n chunks of square root of n size each. And I'm just going to hash each chunk with a collision-resistant hash. I create these square root of n very small hashes, and that's my commitment, size square root of n. And then to open it, so to verify this commitment, the verifier is just going to check a random chunk of x prime. So he has this x prime, which might or might not be equal to x. He takes a random block of x prime and just recomputes the hash and checks that it matches the hash he got. So this requires square root of n queries because this block is of square root of n size. And we're going to actually repeat this a few times at, say, security parameter times. So he checks security parameter of these blocks, or 1 over epsilon, or something like that. Okay, so this is the length of the commitment is square root of n, the number of queries of square root of n, ignoring security parameter factors. And what about binding? So here, if v accepts, you know that the number of blocks where x and x prime are different is at most a constant fraction. Otherwise, you would, with good probability, pick one of the blocks where they differ. And therefore, you also ensure, so constant fraction of blocks also translates into constant fraction of bits where they're different. So you also ensure that they cannot be more than a constant fraction apart. X and x prime cannot be more than a constant fraction apart. But you cannot ensure that they're like really, really close. Maybe if they only differ into like 2 square root of n positions, it could be just the first 2 blocks, and it's very unlikely you would pick those. Okay, so this gives us like this constant distance, but we want to do better. We want to guarantee this epsilon from a constant epsilon to just 1 over square root of n. Okay, so to fix that, we're going to do, say it again? Okay, so to fix that, we're just going to apply an expander graph. Instead of mapping individual, like the first block of x to the first hash, we're going to use an expander graph to decide which bits of x get mapped to which hash, get hashed by which hash. And this expander graph will have a constant degree on the top and order of square root of n degree on the bottom. So essentially, each bit is mapping to just a constant number of these hashes. And each hash still gets order of square root of n bits mapped to it.
It's very similar to distance simplification to the extent coding theory. The error is concentrated and you want to.
Makes sense, yeah. And the analysis is actually extremely simple. So if you have some even square root of n fraction of errors between x and x prime, I'll just draw them here, but they can be anywhere, then by the expansion property of the graph, these errors get mapped to a constant fraction of these two, roughly order of square root of n of these blocks. So a constant fraction of these blocks, not just one block or a small number of blocks as before. Okay, so the errors will kind of propagate into a large fraction of these. And if any neighbor of the errors is checked, then you're going to catch this. Okay, so the verifier is going to catch even square root of n errors. So the expansion property guarantees that any square root of n Hamming errors here get mapped to order of square root of n neighbors. And if you check any of these, you'll catch it. So you'll catch with large probability if you check like just security parameter of these hashes.
Can you get around the explicit construction issue by just amplifying, like picking several times, because you don't have the completely explicit
we do have good explicit expanders for this with these parameters, actually. Yeah, with these parameters we do.
Wait, do you need explicit expanders?
Or
should
good.
you just do random?
Or maybe you have 0.
Yeah.
They have a
But it's long.
could, let's see, we could put, I think, the graph in the CRS, but we don't want a huge CRS, so we can do, and we have explicit.
I think Benny has like very good, like a small.
Yeah, they have only very, yeah, there's issues.
So
Right?
you could amplify, right, if you don't.
But anyway, we have these explicit determinists, we can take them off the shelf. Let's not,
But I'm confused about why, because if you have unbalanced graphs, bipartite graph with constant degree on one side, so do you relax constant to logarithmic? And then
I think the,
Get square root log n.
yeah, the, I'm not sure, but,
I think that with constant degree on one side, it's open. Like, maybe log degree is fine for you,
Even
right?
if you have square root of n log n.
we have a reference in the paper where we claim that this has been done. I'm pretty sure it has, but
So the degree is 3, what's the degree on the constant side?
I don't know what the constant is. But I believe it's constant. Maybe we're hiding log factors. I don't think we care about that. Like if it's log, because all of these are O tildes, we can hide log factors.
That's Tashma woman's.
Okay, so then yeah, I'm okay with height. So maybe that's I'm cheating with the order of 1. It's really the order of log n. Good. That doesn't really affect anything. Okay, so that gives us this commitment of proximity. So now let me show you how to take a commitment of proximity and use it to get an adaptive snap. I'm going to give you kind of a simple construction, but I'm going to rely on strong assumption, and then we'll have to fix it. So here's the construction. At least this should convince you that this is possible. And then we'll try to do it under nice assumptions. So the construction is the prover will take this commitment of proximity and compute a commitment to X. And then he's going to use a snark. So snark here is an argument of knowledge for NP. That's our strong, big, heavy hammer assumption in this first attempt. And give a snark that proves that there exists some X in the language that would map via the commitment to C. He knows an X, that he knows how to open this commitment to some X. And he sends this commitment C, and the snark, the verifier just verifies the commitments C against the statement X prime that he's trying to verify, and checks that the snark verifies as well. Okay, and here's the soundness analysis. So because of the soundness of the snark, we know that if the snark verifies, then we can really extract out the prover has to know an X that is a preimage of the commitment. And then, and it's in the language, and moreover, because of the binding of proximity of this commitment scheme, we know that this X has to be close to X prime. We actually even know that it's very close, but here for this construction, we would have been okay with constant distance. Later we won't. Okay, so that's the whole thing, but relies on very strong assumptions, snark for NP. Can we replace the snark for NP with standard assumptions like maybe snarks for P? Okay, so I'll try to do this in a couple of steps. And the first step is I want to strengthen the notion of commitment of proximity. Essentially, I want to take the extraction from the snark. I want to move it out of the snark and put it in the commitment of proximity. And we'll see that it'll actually be easier. So I want to define a stronger notion of commitment of proximity that I'll call extractable commitment of proximity. In a standard commitment, so in the basic notion we saw before, it says that if you produce X and X prime and a commitment of X verifies with respect to X prime, then X and X prime better be close. In the new notion, I'm going to consider an adversary that produces some commitment C of, and I don't know that he produced it honestly. It might not be a commitment to any X, just produces some commitment C and X prime. And if the commitment verifies with respect to X prime, then it should be possible to extract an X from X prime that's very close and is the correctly committed value. And the reason, again, extraction here is easier than the snark. In the snark, you don't have anything to extract from. You can just extract from the, do knowledge extraction from the prover, right? You can't black box extract from the proof. But here we have the X prime to extract. We have something that we can extract from. We have this big statement X prime that we know the commitment verified against, so we can extract X from that. That makes our life a lot easier. Okay, so the goal is to build, we'll want to build this extractable commitment. Let me first show you if we had an extractable commitment.
Can you repeat the last point? What is flexibility here?
Oh, the flexibility is when I say we can extract X No, we extract x. So we have x prime. Okay, so C is this adversary gives us C and x prime. C is something, we don't know if it's a commitment to anything, it might just be badly generated. But if it verifies with respect to x prime, if the verifier says, yes, I like this, then from x prime, we should be able to extract x, which is close to x prime and is the correctly committed value.
The extractor also has some linear access to x prime?
No, the extractor sees all of x prime, right? I'm saying that if this works, then there really exists some x that the committer committed to honestly. If you verify, there's a good x that you committed to, and I can extract it. And it's close to the x prime.
So basically, but okay, if the delta here was 0, then you're done. It's x prime.
Well, hold on. No, making it 0 makes it all the harder. I cannot extract all the entire. Yeah.
I guess my point is, okay, no. So what I want to say is, it seems to me like the commitment here will need to be at least size square root n, because you'll use the commitment.
Correct.
To correct.
Correct. So you're right. You're exactly on the right track. So first of all, by the way, we already know the commitments to be of size square root n even here. So it's not like we're making it. We're not adding anything for that. But you're right. So that's kind of the intuition. They're already here. This part guarantees that there's like square root of n errors, and will somehow be if you have square root of n information to tell me about these errors, I'll be able to extract. To correct the errors. You're getting a little ahead.
If the only thing you gave me is that the distance is n to the 3/4, then it seems you'll need...
Correct. So you're right. So this is exactly why we needed the basic scheme to have this small distance square root of n rather than epsilon n to be able to correct you. You're getting a little ahead, but yeah, you're right. That will be that will make this possible. Okay, but is the difference between these two notions clear? Here we kind of really assume that the commitment is computed honestly. Here we have no idea, and we're still able to say something. Okay, so I want to show you that if I had this type of extractable commitment of proximity, then I can use standard assumptions to upgrade it to a snap. The idea is similar to before, but now instead of a snark for NP, I'm just going to use a snarg here to do what I did before. So I'm just going to use a snark to prove there exists some x in the language such that C is a commitment to x. It's not a snark for P exactly, but I'm going to use what's called a RAM snark for P, and luckily Omer already told you what that is. Essentially, it ensures that if I have some commitment to x and I know it was generated honestly with respect to x, I know an x that it has been generated with respect to, then if you prove some property of x, it has to be true. So here, I know I can extract, because this is an extractable commitment, I can extract x from x prime and C if the verifier accepts. And then the RAM snark security guarantees that x has to be in the language. It's close to x prime and has to be in the language. So that's enough. Okay, we can use standard assumptions. So now the hard part is, how do we construct this extractable commitment of proximity? Yeah.
Very good distance guarantee is inherited by the snap.
It is, yeah. Even if you don't, we kind of
want it, you just
exactly. You're right, yeah. Good, and it will be in our eventual construction as well. Even if that wasn't kind of your goal, you get this better thing.
And somehow, like the lower bounds are not so sensitive that if you didn't care that much about distance guarantee, doesn't really change.
Good. No, the lower bounds hold even for this any constant fraction, but the positive result actually even gives us like very close distance. You're right. There's kind of a gap in the good way. We get a better positive, like the positive result is kind of, once you get to square root of n, you can get really good distance. Below square root of n, you can't get any reasonable distance.
And going from a snap to this commitment of proximity is like the other direction to see that it's a...
Good question. I'm not sure about that. Yeah, I don't know if it implies it.
The question is, how do you go from a snap to what?
To a commitment of proximity. But the basic commitment of proximity, we at least showed under very simple assumptions, just collision-resistant hashing. So,
is that required?
But,
Is that required?
I don't know. Good question. I have no idea.
Required for what? For the primitive or?
Yeah, for the primitive, for snaps, I don't know if
I'm
collision.
asking both of them.
So
Yeah.
we do have examples of statistically sound snaps. Some problems.
I see.
Even
But
snarks,
for-
we
but
don't-
But even, yeah, we don't really know much about what's required for things like snarks and snaps, what assumptions are required. Like the collision resistance is required or anything, we really don't know. So
It
these are
sounds
great
very
questions,
similar
but
to like the commitment to proximity. Sounds very related
yeah,
to
but
collision.
I don't think we can show an implication that snaps imply collision resistant hashing or
Depend on the
commitment to
language,
proximity or anything.
Depend on the language of languages.
Yeah, even for all of NP, even snarks for all of NP, I don't know that they imply much. Good. Okay, so how do we construct this extractable commitment of proximity? And again, I'll show it to you in a couple of steps. So kind of Yael already hinted at it. One of the tools we're going to use is some sort of error correction, namely syndrome decoding. So syndrome decoding lets us take a long value x and compute a short syndrome. This is the same as parity check information in error correcting code. It's a short syndrome of x in such a way that if I give you any x prime that's close to x, that has at most d Hamming errors away from x, then together with the syndrome, I can correct out the errors and recover x. So the syndrome is some small information about x that together with anything close to x lets me recover original x. Okay, and the correctness, yeah, this is the correctness guarantee. And for us, we'll care about like this d being exactly square root of n. Being order of square root of n. And the succinctness says that we can do this where the syndrome size is roughly proportional to the number of errors I want to correct. So if I want to correct square root of n errors, I just need square root of n size syndrome. Okay, so let's now try to convert basic commitment of proximity to extractable commitment of proximity. You see it says first attempt, so it won't quite work, but this is our start. Okay, so here's the idea. I'm just going to take a basic commitment of proximity, compute it on x, and then in addition, add the syndrome of x that lets me correct square root of n errors. And I'll just send these two things over. And then the verifier will just check this commitment against his x prime. And that's it. And the extraction, I claimed that I should be able to recover x by just decoding from the syndrome and x prime. If the proof verifies, I should be able to decode. So people are frowning. Remember the first attempt. It's not going to work, but let's see. So actually, this does gives us something interesting. Not quite what we wanted, but something interesting. If the commitment, if this was computed honestly, the CNS were computed honestly, then actually the extractor works. So at least I get some sort of extraction from honestly generated commitments, which is already stronger than the property I had before that didn't have any extraction, right? But what if the commitment is, how do we extract in general from a generally computed commitment? And of course, there's the simple attack. The malicious committer just can send a bogus S, doesn't have to match it with the X at all. So there's really no good guarantees here if the committer is malicious. So the idea is let's attach some sort of a RAM snark that says there exists an X such that C is a good commitment of X and the syndrome is computed correctly on the same X. This will try to like tie the commitment and the syndrome together. I'd like to say that this is secure even if the committer is malicious, I can really extract out. But there's kind of this circularity, like if I could extract from the syndrome and really recover X, I would know that this correctness holds. And if this correctness held, then I would know that I can really extract from the syndrome. But there's a circularity here. I can't really guarantee that either of these properties hold. So I'd have no idea how to prove this secure. Okay, so how do we really do this? How do we do it? Well, I'll say, at a very high level, we use a lot of snark gymnastics. This kind of goes back to Omer's talk, trying to get properties of extractability by using standard assumptions. Sometimes you can do it by using a lot of, by playing around with things and kind of doing a lot of tricks. That's essentially what's going on here. I'll try to tell you some intuition and a little bit about how this works, but this is really the most involved part of the paper, and I don't think I'm going to be able to tell you all the details. Maybe at a super high point is we throw everything at it, like everything but the kitchen sink. So we use the syndrome, RAM snarks I already talked about, and also some somewhere extractable hash functions. And very high level, I'll tell you a little bit more in the details on the next slides. but we're going to do the extraction in parts. We're going to have different hybrids where we're going to use some somewhere extractable hash and make it extractable on different parts of xi of x in different hybrids. This is kind of similar to what Omerstog was doing by stitching together different hybrids where you can extract different parts. So let me just, we'll try to make the hash extractable in different parts. Then we'll use Ramsnarks to argue that on the part where it's extractable, the syndrome has to be computed correctly, and I'll be able to extract that part correctly. And then we switch the hybrid to make it extractable somewhere else. But remember, we're extracting now using the syndrome, so when we switch the extractable hash to extractable somewhere else, that has to stay. We still have to extract correctly using the syndrome. So that's the high-level idea.
Yeah, I just want to make sure. There's been several definitions of random snark. Here for Soundness, you assume that you know the instance. That's your definition.
Yes, that's our
Soundness,
definition.
assuming you know the
Soundness
instance.
only holds if you know an x. Yeah.
Do you think you need more than collision-resistant hashing for this notion?
For the extractable, I have no idea. Yeah. I have no idea how to do it without, we're using heavy machinery, and it's an important question to us. Is it really necessary? I have no idea. We thought about it, we couldn't really do it otherwise, but yeah, I encourage you guys to try. It would be, this is the hardest part of the paper, the most technical part, so it would be nice to do it without it. Okay, so let me tell you a little bit more about how to do this in the next few minutes. Just maybe I'll recall the notion of somewhere extractable hash. It's a 2-to-1 hash that maps 2 input blocks, the red and blue block, to one output block, a purple block. And I can set up this hash function to be extractable on either the left or the right, either the red or the blue input. So there's kind of 2 keys, a left key and a right key, and you cannot tell which one is which. You cannot tell between a key that makes it extractable on the left versus the right part. And if I give you the left key, then given the output of the hash, the purple output, you will be able to extract out the left child, and vice versa. If I give you the right key, you'll be able to extract out the right child. Okay, and furthermore, this is RAID 1, which means that the hash value, the output of the hash, is roughly the same size as one of the children, plus security parameter. Okay. So using this somewhere extractable hash, let me give you at least a non-trivial extractable commitment of proximity that's only slightly succinct. The commitment is only slightly smaller than the input, only by a factor of 2. And then we'll try to upgrade it. And we're going to use some sort of a 2-level Merkle tree of these somewhere extractable hashes. So here's the idea. I'm just going to take X and split it up into left block, right block, left block, right block, and do kind of one level of Merkle tree. So hash each 2 adjacent blocks into one output. And all of these purple roots will be part of my hash. So I'm only compressing by a factor of 2. And then I'm going to take all the left children and give you a commitment of proximity for them and a syndrome for them. And I'm going to do the same thing with the right children. So I'm going to compute separate commitments of basic commitment of proximity and syndrome for both parts. And lastly, I'll give you Ramsnarks, 2 Ramsnarks showing that all the blue stuff was computed correctly and all the red stuff was computed correctly with respect to these roots. Okay, so Ramsnarks kind of only ensure that if I can extract, if I know the pre-images of the roots that they're touching, then they have to be correct. Okay, and the verifier just verifies all these components, verifies the 2 commitments of proximity, verifies these Ramsnarks using the roots. So now, so now I claim we can actually prove security here in 2 parts. We can extract in 2 parts. First, I'm going to make the root extractable on all the left blocks. So now I have a separate way, an external way of figuring out what all these blue values are. And so I can use the security of this blue Ramsnark to argue that the syndrome and the commitment of proximity were computed correctly with respect to whatever I computed. And then I can argue that using the syndrome, I do extract out the correct left part of X. Then I switch it to be extractable on the right part. I know I'm still extracting correctly, otherwise you would distinguish, because I'm no longer extracting using the trapdoor, right? There's always the catch. I cannot like extract using the trapdoor and then switch the mode. But now I'm not. I'm extracting using the syndrome. So I can switch the mode, make it extractable on the red part, and do the same analysis again to argue I can extract out the red part. And finally, so this is only compressing by a factor of 2. If you want to do it all together, we're going to have to build a whole Merkle tree, a full Merkle tree, and do everything level by level. So at every level, I'll give you the commitment, proximity, and syndromes for each layer, for all the left children, all the right children separately. And I'll give you the RAM snogs that they were computed correctly. And we're going to do the extraction level by level. First, I'll argue that you can extract like the top level, then the next level, then the level underneath. And essentially, the proof from the previous slide says if you can extract one level above, then you'll also be able to extract the level below. This is pretty hand-wavy. There's a bunch of things missing here, but hopefully this gives you the intuition. OK, so I have a couple of minutes left. I wanted to just tell you a little bit about the lower bound. Why can you not do better than square root of n? And so first, let's talk about a hard problem. So I want to come up for some language for which you cannot have these snaps, some P language for which you cannot have the snaps. Let me first kind of look at a simpler problem of property testing. Property testing is kind of like snaps, except there's no proof. You're just supposed to look at the statement and check on your own if it's true or false. So let's talk about a language where property testing is hard, where you cannot check whether it's true or false just by reading a few locations. And you can come up with many examples, but here's one kind of natural one. Let's talk about secret sharings. So the language will consist of all secret sharings of 0. I'm thinking of some secret sharing scheme where the shares are bits, and there's a lot of redundancy, meaning that a good secret sharing of 0 is far, like epsilon far from a good secret sharing of 1. And there's a large amount of secrecy. Maybe any constant fraction of the indices don't distinguish between 0 and 1. Well, I claim it's easy to see that property testing fails if I only query a bunch of bits of this string. I have no idea if it's a secret sharing of 0 or 1. That's what secrecy guarantees. So I cannot distinguish. I cannot tell. Right? Easy. So again, there's a simple attack. Any verifier that would accept a secret sharing of 0 would also accept a secret sharing, a random secret sharing of 1. OK, but now there's no proof. In this case, there's no proof. Now, what happens when we are looking at the snap case? So in the snap case, the prover can give me some information that depends globally on the entire secret sharing of 0 to convince me that's a secret sharing of 0. Right? So it gives me some proof pi that depends on the whole thing. And now I can't no longer argue that kind of these positions are independent or don't tell me anything because the proof pi can tell me some information. So how do we handle this proof pi? And essentially what we show is this kind of indistinguishability property. So for property testing, we have the trivial indistinguishability property that a random secret sharing of 0 is indistinguishable from a random secret sharing of 1 for queried bounded adversaries, right? If you only query bounded shares, that's just the secrecy of secret sharing. We're going to show that the same thing holds if I allow a proof. So in particular, a random secret sharing of 0 and a correctly generated proof that it's a secret sharing of 0 are indistinguishable from some secret sharing of 1 and some proof that looks like it says that it's a secret sharing of 1. OK, so in particular, if the verifier accepts this case, which he should by completeness, then he'll also accept this case, which breaks soundness. And in particular, let me just say, so for the parameters, this holds if the proof size times the query complexity is sublinear in n. Yeah?
Which parts of the statement are computational? Like, does pi star is the indistinguishability in that second statement also?
Good. Everything is statistical. Everything is statistical. But one important part is that this distribution can be generated efficiently. So that's the computational part is kind of in the good sense that I also need, because this will be my attack, I need this to be doable efficiently. And roughly this, the way we kind of choose this x star pi prime will be just by choosing an honest x, which is a secret sharing of 0, generating a proof pi, honestly, that is a secret sharing of 0. And then that'll be our proof pi star as well. And then we're going to modify x to x star to some secret sharing of 1 by flipping a lot of bits of x. Which bits do we flip? Well, we're going to show that there's some large set of bits that you can flip that are not determined by the proof pi. Essentially, because the proof pi is small, can't tell you too much information about all the bits. There's a large set of bits that you can flip without being caught, while still making sure the proof verifies. So I'm not going to tell you all the details, but essentially the analysis is almost exactly the same as techniques that were used to analyze security in the auxiliary input random oracle model. Those look like very different things. But the statement is very similar. In the auxiliary input random oracle model, you're showing that if I give you some small amount of information about an entire huge oracle, and then you make a few queries to the oracle, there's only a few bits of the oracle that are kind of fixed by this auxiliary information. Every other bit you can just resample at random. So this is the same thing here. We're saying if you get a small proof pi star about the secret sharing x, there's only a few bits of x that are fixed by the proof pi star. You can flip most of the other bits, and you can resample them and not get caught.
Are the shares bits?
The shares are bits. Yeah. Yeah. Let's think of the shares as bits. Good. So so that's the high-level strategy how to prove this. And the parameters exactly come from these types of proofs of auxiliary input random oracle model. OK, so that's pretty much what I wanted to say. Let me just leave off with a few future directions. So one, it'd be very interesting to look at snaps for other distance metrics besides Hamming distance, maybe like L2 or L1 distance, edit distance. We have this square root of n lower bound, and we showed some particular language in P for which it holds, the secret sharing language, but maybe you can circumvent it for specific languages that don't look like this. So it'd be interesting to try to circumvent it for special cases of languages in P. And lastly, I think it'd be very nice to try to come with other applications of snaps or these commitments of proximity, which seem like they should be really useful.
Through conventions, there's quite a bit of literature on achieving for special cases. Better results, polylog, and so on.
For which one?
For circumventing the square root n lower bound.
For the proofs, or for this, for the arguments, or for the
proofs?
For interactive
in particular, it's you get statistical soundness. So you can
for interactive proofs.
Sure.
Yeah.
No, also for non-interactive.
Oh, for non-interactive.
I have a paper with Tom that studies the non-interactive cases.
Okay, nice. Thank you. Yeah. Great. All right, so let me have it.
So what do we know about snaps in the random oracle model? Like, do they exist unconditionally?
Good question. Yeah. So for so I showed you a construction from these commitments of proximity plus snarks for NP. In the random oracle, you get snarks for NP for free. So
right, but not commitment.
No, but the commitment proximity only uses collision-resistant hashing, so you also get those.
No, I'm saying like no other unconditionally in the random oracle.
Yeah.
No.
Oh, I see.
You
Because
can't do a proof about the
good. You're right. So yeah. So there, I guess you're right. We would need to use the.
You have it because there's a paper of Guy, Celine, and Avi, and then a paper of the Rothblum brothers that do interactive proof of proximity with these parameters, and then you can just apply random oracle model.
I see. You can just compile it into.
Yeah. So similar parameters. So actually, I was,
hold on, but so you're thinking of Fiat-Shamir, right? But then you have to, in the adaptive setting, that has the issue.
in the non-adaptive setting.
Good.
Yeah.
So in the non-adaptive setting, right? You can just use like Killian-style protocol with proofs of proximity, with probabilistic check of proofs of proximity. You're done, and Fiat-Shamir. But the Fiat-Shamir part really does not work for adaptive. You have to share the statement. You have to hash the statement. So I thought you were asking about adaptive. Then I don't know. I guess. We have it from collision-resistant hash function plus random oracle model,
right?
But not just random oracle. Yeah.
So would it be just only want to simplify the commitment of proximity using random oracle? I mean, instead of this snap for P, does it get simpler at all?
Yeah, good question. None that I know of. Like, so
Couldn't
for
you get a snark for NP and use that inside the warm-up?
Say it again?
Couldn't you get a snark for NP?
Yeah, right. So, right. So, yeah, but then you're doing a proof over the, you're still doing a proof over hash function. So you're using a hash function in non-black box way. Yeah. So I don't know how to avoid this non-black box use of the hash function.
It's kind of weird at the syntactic level that PCPs of proximity don't show up anywhere in the talk. So yeah.
I agree. Yeah.
So I guess it's also natural to try to generalize the access model to the string rather than just accessing points in the string. Maybe you can treat the string as a polynomial and you can evaluate it at random points. This is going
Great
back to
question.
Ali's first talk.
Yeah.
Functional access to the string. So
Yeah. We haven't thought about it.
there's some results actually.
Yeah. I assume you might be able to do much better than just proximity, but you might even be able to get like the real sound, full soundness, depending on the Oracle model. Yeah.
So what is the notion of errors? If you do like polynomial access or whatever, one access is, what is the notion of
Yeah, so-
You need to check that the commitment is consistent with the
still can be this?
Yeah, potentially you could have no errors.
No, there's two issues. There's the error model and
Yeah.
the query model.
Yes.
Two separate issues.
Yes. I'm saying for strong enough.
If you go back to your previous slide,
For strong.
like your first, you try to generalize the error model in your first book.
Yeah.
But you can
No,
generalize the query model.
Right. So I'm saying for strong enough query models, you can maybe even get rid of errors, get
yeah.
full soundness,
Yeah.
right?
Because
Potentially.
if you're at the encoding,
Right. Yeah, but we haven't thought about it yet. It's a good question.
Yeah, exactly.
Yeah.
That's exactly what I was referring to.
For example, if it's linear, maybe you don't need errors at all, right? Because you can kind of ask code what's right away.
Exactly.
any other questions? Thanks so much.